This presentation is part of the WEC-Sim training course. My name is Jorge Leon. I work for Sendia National Laboratories and I am part of the WEC-Sim development team. In this presentation, I'll be focused on one of the advanced features of WEC-Sim, which is PTO Sim. Well, first of all, what is PTO Sim? What is its purpose? First, let's consider the equation of motion in the time domain for a floating body. This equation of motion has different terms such as the hydrostatic restoring force, the wave excitation and diffraction force. That force is calculated based on the boundary element method simulation results. We have also the radiation force, the added mass, and the radiation damping. That force is also calculated based on the boundary element method simulations. We have a viscous force, a power takeoff force, mooring force, and the nonlinear hydrodynamic force. So the purpose of PTO Sim is to calculate the power takeoff force in this equation. Usually, the PTO is represented as a spring damper system for simplicity, which can be modeled using this equation presented below. This is a linear equation, but the idea of using PTO Sim is to be able to model nonlinear PTOs. PTO Sim is a package of detailed PTO models. It is open source and it is integrated with WEC-Sim. It is open source because it is written using the basic Simulink blocks. So if you have a basic MATLAB and Simulink license, you don't need to pay extra to use PTO Sim because it is based on what it is included when you have a basic Simulink and MATLAB license. PTO Sim class includes models such as hydraulic cylinders, hydraulic accumulators, hydraulic motors, electric generators, and hydraulic valves. And there are other packages or toolboxes within MATLAB that can be used for this, such as Simscape Hydraulics and Simscape Electrical. But these toolboxes have additional cost. And so the purpose of PTO Sim is to provide a reliable and open source package to model PTO systems. How can we use PTO Sim within WEC-Sim? So let's say that we have a regular WEC-Sim model, such as the one that I am showing here in this slide. What you need to do first is to select an appropriate PTO, either rotational or translational, and then you need to create a subsystem for your detailed PTO. The input is the response, and the output is either the force or the torque in the PTO, depending on the one that you selected, rotational or translational. And then this subsystem can be edited depending on the desired level of detail that you want for your model. Here in this subsystem is where you need to use the PTO Sim blocks. PTO Sim has a library with 10 blocks grouped in 3 different categories. We have electric, hydraulic, and motion conversion subsystems. So then if you go to the Simulink library browser, after you install WEC-Sim, you can see the different sub-libraries that we have within PTO Sim. These are the blocks that we currently have in PTO Sim. So for hydraulic systems, we have a compressible fluid piston block, a gas charge hydraulic accumulator, rectifying check valve, a hydraulic motor, and a regular check valve. For electric systems, we have an equivalent circuit model of an electric generator. we have a direct drive linear generator and a direct drive rotary generator. And for the motion conversion blocks, we have two blocks. We have the rotary to linear adjustable rod and the rotary to linear crank block. And I'll talk about these blocks with more detail in the next slides. Let's consider one example. We are going to consider the RM3 with a hydraulic PTO. The RM3 is a tube body point absorber, and this is the hydraulic PTO that we are going to consider as an example. And we are going to illustrate how to use PTO Sim to model this specific hydraulic PTO system. So here what you can see is the float that is connected to a hydraulic piston. This piston is connected to a hydraulic system that is converting the vertical linear motion of the float into a rotational motion for the electric generator. So we're going to see how to model. This is how the PTO subsystem will look like after we drag all the blocks from the PTO Sim library. So here you can see the hydraulic cylinder. The hydraulic cylinder is receiving the response as an input. This comes from WEC-Sim. Then we have the rectifying valves. We have the two hydraulic accumulators. One is the high pressure accumulator, the other is the low pressure accumulator. We have the hydraulic motor, and this hydraulic motor is connected to the electric generator. This is an equivalent circuit model of an electric generator. And here we also have a control algorithm. This control algorithm is used to control the speed of the electric generator here. After you drag the blocks into your subsystem for the PTO, you need to define the variables associated with each block. So then, for example, here in the compressible fluid piston, so if you double click this block here, this is what you can see. Then you will need to define the name of the block. So in this case is PTO Sim 1, and then you will need to define one specific name for each of the blocks that you are going to use. So for example, the piston name is PTO Sim 1, but the hydraulic motor block name is PTO Sim 5. So you will need to define these names for each block. And then in the WEC-Sim input file, you need to define and you need to initialize the PTO Sim class. And you need to use the names associated with the specific block that you need or that you want to define and model. So for example, for the hydraulic cylinder, so it's PTO Sim 1, so we need to initialize the class with this line here. So we need to call the PTO Sim class, and we need to write the name of the specific block, which in this case is the hydraulic cylinder. And you can see here how we are initializing the PTO Sim class for the hydraulic motor. And then after that, after you initialize the block, you need to define the different parameters of that specific block. So for the hydraulic cylinder, for example, we have variables such as the initial position of the piston, the areas in the piston stroke, the initial pressure in both chambers, etc. So and for each block you need to define the specific variables associated with the block and with your application. These are the hydraulic accumulator blocks. So in this one you need to be careful with the positive convention of the flow in the accumulator. So then, as an example, I took here both accumulators, the high pressure accumulator and the low pressure accumulator, to illustrate how you need to define the signs in your flow, right? So for example, I have taken this from the from the hydraulic system. And then in this node, what I can see here is that I have a flow C coming here from the rectifying valves, and I have some other flow here going to the hydraulic motor. So then, based on the conservation of mass in this node, I can define this equation here for the flow in the accumulator, and then I need to add one block here to calculate that flow in the accumulator based on this equation, and this equation is based on my specific application and the specific configuration of my hydraulic system. So here we can see the difference with the low pressure accumulator. In the low pressure accumulator, the flows have like different directions, and if I apply again the conservation of mass here in this node, this is what I can have to calculate the flow in the hydraulic accumulator. And that's why I need to put this block here to calculate the flow in the hydraulic accumulator based on this equation and based on the specific application that I am trying to model. Another aspect that we can model here in this example is a control algorithm for the shaft speed in the electric generator. So here we have the block for an equivalent circuit model of an electric generator. This block has as an input R load, which is the load in the generator. This load is variable and it can be adjusted by the user. For example, in this case, to adjust the speed in the system. So then this control algorithm is changing the value of the load in order to control the speed in the generator. So R load represents the load in the generator, and R load is used to control the shaft speed in the electric generator. So remember that this example, the complete example, you can find this example in the WEC-Sim applications repository. Some other examples that you can find in the applications repository are, for example, this oscillating source wave energy converter. This example has a hydraulic cylinder connected to an adjustable rod. So as you can see, this is a schematic representation on how the oscillating source wave energy converter moves, right? How the angle change in this example, and how the hydraulic PTO, and specifically the hydraulic cylinder, is attached to this rod, right? So then you can see here, as the system, as the OSWEC moves, then the length of the road changes, right? So then you can model that also in PTO Sim by using this block, the rotary to linear adjustable road block. So you need to connect that before your hydraulic system, and it is in this example the hydraulic system is exactly the same as the one that I just previously mentioned, but in this case we need to put this motion conversion block to convert the rotational motion of the device into linear motion in the road, right? Another example that we have, similar to the one in the previous slide, is the OSWEC, but with a hydraulic cylinder rod connected to a slider crank mechanism. So the difference here is that the hydraulic PTO cylinder is connected to a slider crank mechanism. So in this case, the rod has a constant length, and what is changing here is the length of the cylinder in the hydraulic PTO. So then here what you can see is an schematic representation of the system, of the movement of the system. So as you can see here, when the flap moves, right, this angle change here, the length of this cylinder, of this rod, sorry, is constant, but the length of the hydraulic cylinder is not constant. So you need to use a motion conversion block to convert the rotational motion into linear motion in the hydraulic PTO. So this is the other example that you can find in the WEC-Sim applications repository. And that's all for this presentation. Remember that all previous webinar materials and recordings are available online in the WEC-Sim webpage. And thank you.